Alright, so this video is going to cover some of the more difficult problems in the textbook. So we're going to first look at this problem number 35 under preparation. I know it's preparation, so it's not that big of a deal, but we're gonna look at it anyway because it's so difficult. Oh, looks like I'm in full screen. Alright, so the problem says 5a to the negative 4. B to the negative 7. C, and then D, and then I think it goes up to F on the top there. And it says negative 3, negative 5, negative 9. And then on the bottom, it says 7G negative 3. Eight H negative 8. And J negative 2 and K negative 1. So the first thing you'll notice about this is there's no variables that match between the bottom and the top. They've done sequential letters and nothing matches between the bottom and the top. So that's the first thing we realize. And then what we need to look at is that these negative exponents, in order to make them positive, they go on the bottom. These ones on the bottom, in order to make them positive, they go on the top. So what we're going to do is we're going to say this is going to be the 5 and the 7 don't move. They stay on top and on bottom because they don't have any negative exponents attached to them. The only ones that do are all these letters. So this becomes 7a to the 4th, ba to the 7th, or b to the 7th, c to the negative 3, or c to the 3, c cubed. Sorry about that. C cubed. D to the 5th, f to the 9th. So in order to make those negative exponents positive, they went on the bottom. That's all that happened there. This one, on the other hand, they go to the top. So we're going to say G to the 3, H to the 8, J to the 2, and K to the 1. So this problem, although it doesn't have an answer in the book, the answer is this. Because negative exponents, whenever you have a negative exponent on the top, two to the negative x will always be 1 over 2 to the x, and 1 over 2 to the negative x will always be 2 to the x over 1. So that is how you know the difference for your negative exponents, and that's described in another video, why they're negative. All right. Now we're going to go to work on another problem. Let's simplify the following. Let's simplify number 7. So number 7 says 15c, oops, to the negative 7, d to the 3. All right, so that's d to the negative 3. You're going to then say, or d to the 3. And this is, and then you're going to say on the bottom is 35c to the 5th. All right. So now what we're going to do is we're going to completely simplify this problem, but we have something special in it. This is to the -3. So before we do anything, we're going to multiply all this by that. So how this works is we take our top number. So it becomes 15 to the -3, right? 21. All right, so that, if you see, was where we multiplied this out. And if you remember, a negative times a negative is a positive, so we got positive 21. Now we have to do the same thing to the bottom. So that becomes 35 to the -3. C to the -15. And D to the -21. So now we have to deal with our negative exponents. Now that we have solved this down to that, after applying our distributive property with exponents, our multiplication property, we are going to now get rid of our negative exponents. So 35 to the third. So we're going to flip that to the top. We're going to put 15 down on bottom. Then we're going to take and let's see, C to the 21 goes on top because it's positive. C to the 15 goes on top because it's positive now. D to the 9 goes on bottom. D to the 21 goes on top. All right, now we have to apply a couple different rules. This 15 and this 35 can be broken down, which is 7 over 3. These C's, since they're the same base, right? So if we could go back to our rules here. No, we go back to our rules for exponents. There. This, when they have the same base, we can add the exponents, right? So these have the same base, so those exponents get added, so we get C to the 36. This 3 is still there. We just divided these by 5 because I noticed that 5 goes into 35 and 17 and 15. It could have been done here, and that is why we can do it here, because it could have been done up here. So this is going to be to the 3 as well. This C's get added, so it's C to the 26. Or 36. Right? C to the 36. Minus 21 minus 9. So this one, it looks like this. D over 21. D over 9. If you remember, that means that it's going to be D to the 21 minus 9, right? Because our division rule states we do that. So then this becomes D to the 12. So if we do the math on this, it's 7 to the third, and we may need to break that down for the answer. I'm not sure how they want it, but it's 7 to the third, C to the 36, D to the 12, over 3 to the third. So that is how you would do that complex problem. Remember your distributive property, or the multiplication property of exponents. Then we just divided that by 5 to get 7 over 3. That was nice. But we did our negatives. We solved our negative exponents, put them into positives, and then we combined what we could and simplified it down. So the simplified problem, if we were to look at that simplified problem, oops, I went too far. So it's number 7. Yeah, so what they did is they just took and put those exponents in and just did them in the calculator. Otherwise, their answer is the same. So why doesn't a negative exponent make the answer negative? That's a good question. Let's discuss that real quick. Why doesn't it make it negative? So this problem that we did before was a good problem because it discussed many different ways to use exponents. So I would watch that a couple times until you understand what's going on there. But why doesn't a negative exponent make an answer negative? The simple answer is negatives mean division. So if you have x to the z, so any number to the any number, right? To the negative of any number, it will always equal 1 over x to the z. If you have 1 over x to the negative z, then that will always equal x to the z. Just take this and move it up one level. Take this and move it down a level, right? Anything over 1 is itself, so this also equals x to the z. But that rule is why negative numbers don't produce negative exponents don't produce negative numbers. What if we had this? What if we had a 2x to the negative 2? What would happen there? Let's think about this. The negative 2 only affects the x. It doesn't affect this 2, right? So we know the 2 is going to stay on top when we divide. Now this negative 2 just means the x goes on bottom. Therefore, negative 2 to the x to the negative 2 is the same as 2 over x squared. So that is how that law applies. Because we're working with multiplication, it applies that way. If it was addition, so if it was this way, we could say, yeah, the 2 doesn't have anything to do with it. But we couldn't put the 2 on top. It would have to be 2 plus x squared. That's how that would have to look. Because exponents do not play well with addition or subtraction. They only work well with division or multiplication, and we can see that in our rules. There are nothing that says a to the m plus a to the n equals something. It doesn't do that. Does that make sense? It doesn't do that. There's no rules that say a plus a to the m plus a to the n equals something, because there is nothing. Exponents don't do that. We can't take and say that x squared plus x to the third does not equal x to the fifth. These are two different things. They can't be added. This is your penguins and your cows. You can't add penguins to cows. They're not the same thing. But if it was this times x to the third, then that equals x to the fifth. Because now we're multiplying like things. We're saying that x plus x times x times x times x. Now they're the same. Now we can combine them. We can't combine them before because they're different things. And that's why our exponents are different. So that kind of covers a little bit about some of the harder problems in the book. Let me know if you need any other problems explained, and I'll see what I can do.